lunch talk. And today our first speaker is Dr. Andy Goulding. And Andy is currently an associate research scholar at Princeton University. And he's expert on black hole and the galaxy using multiple-based data survey. And Andy got his PhD and master's degree from University of Durham in UK. And most importantly, he has been a postdoc at CFA for 4 years. And he always wants to come back to Boston area, mostly because he wants to participate in the Boston Marathon. And but before that, he's going to talk to us about the evolution of black holes and galaxies.
Thanks, Ron. Okay, it's very nice to be back at CFA again amongst friends and other friendly faces. So for today, what I thought I would discuss are some recent thoughts that we've been having down at Princeton with regards to, at least from a statistical sense, what causes supermassive black holes that reside at the center of galaxies to actually grow. It's all right actually having the black hole at the center of all these galaxies, but how do we actually make them grow across cosmic time? How do we actually get the gas down to the center of the galaxies to actually accrete onto these black holes? And obviously no research is ever done in isolation, so a shout out to all of my collaborators, in particular my two students, Eve Mate and Tristan Schrader, who've actually been doing a lot of the work, particularly from looking at our latest Chandra paper on galaxy bars, and Tristan has been doing a lot of new interesting work with statistical surveys from Hydra Supreme Cam. So to begin with, let's look at this from a big cosmological standpoint and choose whichever happens to be your favorite galaxy simulation. And we know that through the growth of structure across cosmic time that we have the most massive galaxies, and by extension the most massive black holes, always reside at the center of the most massive halos in these enormous groups and clusters. And in the simulations, we've known for many years that we have this problem that if we just let the galaxies evolve, we end up with extremely massive galaxies at the center of these halos, but they often have too much star formation going on in them. And so we have a lot of gas there, and we somehow need to suppress star formation very quickly, especially, as Bill always points out to me, if we want to understand how something like M87 comes into existence. We know that M87 has to have been in situ very early on in the universe, and the star formation has to have been suppressed very early. And the way we've known about this for many years now, but the way we think we shut down the star formation is through a process through AGN feedback. So basically, you have the black hole at the center of the galaxy light up through accretion, and then you dump a lot of energy back into the ISM and even into the ICM to shut down the star formation and basically heat up the gas, prevent the gas from cooling and forming new stars. And we think, if we just simply take a look at the galaxy luminosity function, that it's the AGN that do all of this feedback, at least at the most high stellar masses, highest galaxy luminosities. And then maybe once you get past this knee in the luminosity function, this supernovae feedback becomes more important. And we've had this kind of picture in mind now, this toy model that if we merge galaxies together, we can make some form of ultra-luminous infrared galaxy, a submillimeter galaxy, just train wreck merger, however you want to think about it. And when this happens, you create enough angular torques within the galaxy that you can dump all of this gas very quickly down towards both central supermassive black holes if it comes from two galaxies, ultimately becoming one single supermassive black hole. You make a quasar, you blow all of this gas out, and then maybe you end up with an early time galaxy at the end of this. And if you want to think about it more from a galaxy point of view, that this is the typical color magnitude diagram that's in around redshift of 1. We have many star-forming galaxies, blue galaxies that reside down the lower portion of this diagram. And then at some point between redshift of 1 and redshift of 0, we know we have to build up this red sequence. And this is where our our AGN fairy comes in, if you like. She comes along, she lights up the center of the galaxy, and we shut down the star formation, and then we bump everything up onto the red sequence. And if we're doing this, we're growing the black hole. And concurrently, you have this picture, whereas if you follow the star formation rate density over the portion of the, over the last 12 or so gigayears of cosmic time, you get to some peak, and then it falls off a cliff as we come down to the present day. And this seems to actually follow the quasar luminosity function very well. So it's suggesting that if you have the star formation going on in these galaxies and you have the growth of the black hole, they somehow know about each other. And of course, we all know about the so-called Magorian plot, where we have the most massive black holes live in the most massive galaxies, the small black holes live in the smaller galaxies. Again, you have this connection between the galaxy and the black hole. And if this is what's going on, that you have the evolution of the galaxy occurring and the black hole growing at the same time, you have this interplay between them. And we tried to actually look for this from an observational standpoint a few years ago. And we actually found that these are just different redshift slices in the same color magnitude diagram, that if we go from roughly redshift 1 down to redshift 0.5 to redshift 0, at every point in time, AGN, these are all the infrared AGN and the red dots here, and the green stars are the X-ray AGN, and then finally at the top we have the radio AGN. The AGN, at least the ones that are the most rapidly accreting AGN, always seem to live in any kind of galaxy in the color magnitude diagram. So either the AGN is actually just going off and it doesn't know anything about the galaxy, or AGN and galaxy activity and evolution is occurring simultaneously to such an extent that it blurs all of this evolution out. The only difference we actually found was with the radio population. We always know the radio AGN always seem to be in the most massive galaxies that they're already in the red and dead systems, which really gives rise to something that we call the maintenance mode, which is essentially that the radio jet is preventing that gas from cooling by just slowly dumping bits of energy back into the ISM. This has been known for a long time, but it already seems to be in situ at roughly redshift of 1. Though one thing that we didn't have when we did this, and we just had to be happy about this, was that we had no idea what the morphologies of any of these galaxies are. So it could be that if you can split this up in terms of, let's say, mergers versus simple spiral galaxies, or already red and dead early type galaxies that are very relaxed, you could see something different. But we didn't have that resolution in the imaging to be able to do something like that. And also something that was missed out here is that because we wanted to see the galaxy colors, we couldn't have the quasars in here. So we had to purposely chop out the extreme tail of the AGN luminosity, or the high Eddington AGN. So if we come back to the toy model that we have, I said that mergers were something that we were putting into the models, or we expected to see in the models, in order to get to this early type diagram, to this early type galaxy. So the question is, if we boost up to these higher luminosities, is this where we start seeing the mergers coming in? And indeed, if you look in the high redshift universe, and you look at the more moderate low luminosity AGN, you see no difference between the number of galaxies that contain mergers if they have AGN, or whether they're just non-AGN type systems. But if you go to the extreme high luminosity systems, then they're actually starting to find that mergers are much more prominent in the high luminosity systems, which gives rise to this diagram that if we come up in AGN luminosity, we see that the fraction of galaxies that are in mergers tentatively increases. And people are starting to build models that go with this. The only downside of all of this is right now is that these error bars are obviously very, very large. And that's simply because we just don't have the source statistics to actually do this very well. So if we actually do want to start asking whether or not there is a morphology dependence here, and whether or not we can actually start pulling out mergers here, we need to actually get into a situation where we have extremely large volume in the relatively nearby universe where we can get very good morphologies. And obviously that's not very easy to do. We know that our gold standard for many years now has been the Sloan Digital Sky Survey. Now, Sloan is absolutely fantastic at giving us morphologies out to about redshift of 0.1. We've got about 10,000 square degrees of sky there, but actually there's not a huge amount of volume in terms of being able to go out into the higher redshift universe. As soon as we get past 0.1, we don't have any morphologies left. Sloan was just never deep enough, never had the resolution to do something like that. In fact, just as an example here, this is, I assume everyone's heard of Galaxy Zoo at some point. This was the citizen science project. If we basically dump all of the Sloan images and let people just go and classify galaxies of their own volition on the internet, then we actually build up a table of what we believe the morphologies of all the different galaxies are. But if you look at something at redshift 0.4, even in, this is a boss image from SDSS DR12, something which is not particularly faint, on the eye of 22, you essentially have no idea what that thing is. So what's the solution to this? Hydra Supreme Cam. This is the same galaxy. So we have the new Hydra Supreme Cam survey, which is now coming online. There's going to be a data release for this sometime next year. This is I can show you a 1400 square degree survey that's basically SDSS on steroids. So instead of going down to I of 20, give or take, is what Sloan goes down to, this will go down to I of 27. It's 1400 square degrees. It gives us many, many millions of galaxies. So Hydra Supreme Cam is actually just an upgrade of the old Supreme Cam survey, which is on Subaru on Mauna Kea. So this was the upgrade. If I just do this very quickly, we basically put a new imager at the prime focus on Subaru, and it's pretty big. 3 meters high, so obviously that takes a lot of structure in order to actually hold that thing up there. And just to give you an idea of how big the field of view of Hydra Supreme Cam is, obviously we have the moon, we have something like the Goods field or the Hubble Ultra Deep Field. This was a single shot Supreme Cam image in the past. This is the field of view of HSC. You get a lot in one shot. What does that give you? This is a one-shot, three-band color image. This is 12 minutes of M31. So you can see the edge of the field of view down here, and you can just see it up there. And like I said, this is what you get in 12 minutes, and 12 minutes is quite pertinent here because this is the depth of the 1400 square degree survey. So if we just zoom in bit by bit, you can see there's a lot of structure, and you can see galaxies even through the disk of M31. You can see background galaxies, and you can see you're resolving out individual star clusters. It's great. Putting this into a little bit more context, these are our past surveys that we know of. SDSS is down here at something like 10,000 square degrees. Being very nice, putting it down at R of 23 here. But these are our wedding cakes, if you like. HSC Wide's 1400 square degrees. HSC Deep is a little over 20 square degrees. And HSC Ultra Deep, which is really cosmos, it goes down to about I of 28. And obviously the main things that come out of this is being able to actually do weak lensing measurements, because the PSF of HSC is only something like 0.4 arc seconds across most of the field. The terrible seeing that we had was about 0.6 arc seconds. Obviously the stuff I'm interested in really is the galaxies, and we can get good morphologies out to about redshift of 0.8 to 0.1. Just in case you want to pick out your favorite surveys here, HSC Wide is this dark, mucky red color that we have here. So there's two main regions that are equatorial. There's Hectomap, which is up here as well. They're purposely put in things like the SDSS surveying in BOSS and Stripe 82, so we can get lots of spectroscopy. They're also in the gamma fields, and then Vikings, UKIDs, etc., etc. What does this really give you? Well, these are about redshift 0.4, redshift 0.5. This is why I always think about this as Sloan at redshift of 0.5 to redshift of 1. These are the same kinds of images that we have from Sloan at redshift 0.05, and we're getting them at redshift 0.5. So this now presents a new problem, that we have so many millions of galaxies that we actually need to process these. We actually need to understand what the morphologies of all of them are. So just as an example, this is what you get from HST, which is obviously such a tiny area in comparison within Cosmos. This is what we're getting out of HSC, and then we're starting to model them with Galfit, and we're actually doing pretty well with these. We're actually finding the disk-dominated systems, and we're getting the bulge-dominated systems out. We've so far processed about 300 square degrees worth of the data. Obviously, still more to do. And what we've been working on actually at the minute is about 120,000 galaxies that we have that all have spectroscopic redshifts. So we can start to do things like understanding the color magnitude diagrams, understanding what their stellar masses are, and then more importantly actually get information about the mergers, which is where I'm going to go in a second. So another example, this is what you get when you have something like Hubble. This is fantastic, but this is what we now get to work with HSC, and we get these low surface brightness tidal tails of these things colliding with each other. This is actually a triple AGN merger. This is a stunning system. So the question is then, how do we actually identify mergers in these things in HSC? We're having to take a very automated route with this. So in the past, what people have done, particularly Chris Contes, Jen Lotz, and others that really champion this, is the idea of using different morphological or distributions of wealth within the images of each of these galaxies. Something like the Gini index, for example. You essentially ask, how well clustered are the bright pixels within all of my galaxies? And what happens when I rotate one image compared to another? You get something like the asymmetry of a galaxy. And you combine all of these different metrics together, whether it's the concentration, if something which is relatively smooth and is centrally concentrated, tells you that it's probably not undergoing a merger. But if there are multiple concentrations in this thing, then maybe there is a merger, or you've got a phase-on spiral galaxy, something like that. And it leaves you in this situation where you have to combine all of these different metrics together in order to get out whether or not you have a merger. And this is what my student Tristan has been working on recently. So what we're trying to do right now is do something like this, where we take a Gini index, which asks about that distribution of wealth, we take the asymmetry, and we actually go through, let's say, a subsample of a few thousand galaxies, nothing crazy, and visually identify whether or not we have a merger going on in these things. And then we plot up these metrics and then ask, is there some kind of cut that you can make in these parameter spaces that would tell you whether or not some probability that you have a merger? And these seem to have been working really well. And what we've now started to do is ask if we can use machine learning to not just ask, do I have a merger, but do I have a late stage merger? Do I have a minor merger? Do I have a major merger? Do I have a first pass? And then we can start breaking things up even more. And we can actually start to do this because we actually have the statistics to do it. And this is the kind of thing that we've been doing. These are all pulled out automatically from the pipeline. And we're not just taking the images at face value, we're actually trying to fit them with simple profiles and then ask how much information is left in the residuals in order to give us that next parameter that we can use in order to pull these things apart. And as a quick teaser, we're actually finding that if you plot up this, this is Y's color 3.4 minus 4.6, so basically how steep your Y's infrared emission is in these galaxies. And if you have something above this particular threshold, which Dan Stern championed over the past several years, then you have an AGN. A little bit further down, you have more things that are starburst dominated, and then you have more regular galaxies live in this parameter space. And we actually find that we have an increased merger fraction in AGN, which is something which has been a little bit controversial over the past few years. Maybe we just haven't had the statistics to do it quite right, maybe we haven't quite had the imaging to do it right, but we seem to be getting somewhere. But something I'll point out here is that I'm still only showing you about 15% of the sample right now. Okay, so that's my merger side dealt with. So I said at the, in my title that I was going to discuss secular activity as well. So essentially, you're asking, what about galaxies? what kind of black hole growth is occurring in galaxies that aren't undergoing mergers. So basically something more like the Milky Way. We know right now the Milky Way is not really growing Sagittarius A star. It's sitting down in a very, very low accretion state. But there are galaxies very nearby which look very similar to Milky Way that are growing their black holes. So what's the difference? Why can you grow a black hole in one and not in the other? And basically the issue that you have is somewhere out here in your spiral arm, you have a large amount of cool gas. This would be a nice fuel to put down onto the black hole. The question is, how do you transport it from here to here? I've kind of set this up by choosing this particular galaxy. And what people have argued for a long time is that something like a bar in the center of a galaxy is a very good way to basically dump angular momentum from this gas and actually get it down onto the center of the galaxy very quickly. But this has been fraught with problems. This is almost like a holy grail of black hole growth, galaxy evolution picture. Let's say you take something like Galaxy Zoo. This is a relatively recent paper by Galloway. They took all of the AGN that they had in SDSS that also had morphologies from the Galaxy Zoo project, and they found a marginal increase in the fraction of AGN that contain bars. This is a positive result. We're happy with this. But if you do this more thoroughly with a smaller number of galaxies, but in a less statistical sense, just a very detailed sense, someone like Mauricio found that there was actually no correlation between the AGN power and the strength of a bar. In fact, there's entire literature on this of people saying yes, no, yes, no, no. Now, the question that I'm wondering, or we've been wondering recently, is are we asking the right question here? What people usually do is they pick a sample of AGN, and then they ask how bar fractions differ within those AGN. But accretion onto a black hole is a very stochastic thing. It can vary hugely by orders of magnitude in terms of accretion rate in very short timescales of under mega years. And you're then comparing it to a stable galaxy relatively stable galaxy property like a bar, which remains in situ for 50 to 100 mega years. You have this orders of magnitude differential in time. So how, by choosing the short timescale object, are you going to ask questions about the long timescale object? And more recently, Mauricio asked this same kind of question. He took the Cosmos field. He was limited by source statistics here, but did a pretty good job of using AGN stacking. So he took the Chandra data and stacked everything up and asked what was the average accretion rate for barred galaxies or non-barred galaxies, which makes much more sense in my mind. The only problem was, like I said, he was limited by the source statistics. So I was like, okay, let's take the two extremes. We have Galaxy Zoo and we have X-ray stacking. Can we actually combine these two things together? So this is what we've done. We took the whole of Sloan, we took all of the Galaxy Zoo morphologies, and we took every Chandra observation that's ever occurred within Sloan, split up all these galaxies into particular bins between bars, non-bars, and then maybe an ambiguous evidence for a bar, and then stacked all of the Chandra data. It basically gives you this. You then normalize out by stellar mass, you take care of your emission from star formation as well, and it becomes very obvious that it doesn't matter whether you look in the soft band, the hard band, or the full band, there's no statistical evidence for any difference between the growth of the growth rate of a black hole and whether or not it contains a bar, on average. So maybe bars aren't really the solution here, but wait. If we then ask, okay, how does my AGN detection fraction change with this stable property? We actually find that AGN are more likely to occur, or detected AGN are more likely to occur in barred galaxies. Okay, both of these two statements can't be true, or can they? How can I have AGN more likely in bars, but the average accretion rate be the same for barred galaxies compared to non-bars? And I think it's a cause and effect. What caused the bar probably caused the black hole to grow. Minor mergers are very good ways of causing bars. Basically, you have that extra torque that comes into a galaxy, which then creates a bar structure in the center. This brings in cool gas that very quickly could end up down at the black hole without using the bar, just because of the exchange of angular momentum. This lights up the AGN and begins to construct a bar. The AGN uses up that gas that it had that appeared there very quickly. The AGN shuts off, but the bar remains in situ. So on average, this is the state that you see over long time periods. But briefly, you get this. And then finally, the bar dissipates and you end back up this. This, I would suggest, is actually our new picture of secular evolution. And I think I'm out of time, so I'm just going to leave it there.
High luminosity picture with a low vision, still only have 20% of the sources big emergence time. So what about the other 80%?
I don't know. Yeah, that's something I purposely skipped over because you can't get away. There's two things. It's the same question on both sides of this, that you have 80% of mergers that don't appear to have extremely luminous AGN in them. But then something like 80% of barred galaxies don't have AGN in them either. And you still have AGN going on in non-barred galaxies as well. Explaining all of these things is difficult. There's obviously more to this picture. This is a partial solution, let's put it that way.
How about a Hopkins and Quaternary type of picture where you don't form bars, but you have a gaseous disk and a stellar disk, and the torques that they apply on one another supply a continuous gas to the centers of galaxies. And you can actually grow black holes in the secular mode very nicely in that picture. We've implemented it into cosmological simulations that black holes grow. So this is not good news for your morphology search, but because it doesn't have either a bar or a actual merger. But what I'm saying is, I guess, if you end up finding that there is no morphological difference between these, there's also another torque scenario that might work.
Yeah, it basically goes on from like Belinda's question that there are probably multiple avenues here. And the idea that you would only grow them without any bar at all seems odd, because then you still come back to the Milky Way and say, well, so why aren't we growing our black hole now? There has to be something which causes that black hole to light up in the first place. And if it was simply this exchange of angular momentum due to the disk, then you would expect concurrent black hole growth in every single galaxy, I should think.
There's a discrepancy in the shape of the luminosity function between the CDM simulations and observations. Do the numbers come out right? Do the total densities?
Depends who you ask. It depends which simulators you ask.
I mean, was that just a pure cartoon where you arbitrarily matched them at the break luminosity?
In Joe Silt's diagram there, yeah, that's really a cartoon, because in a lot of cases they match pretty well at the low end, as far as I'm concerned, as far as I know anyway, from the recent simulations. It's at the high luminosity end where they begin to really diverge, and yeah, it depends how you normalize it. But then we've got so many simulations going on at the minute. It's hard to take them to pieces and understand which one I should really be looking at, right?
Well, let's be clear here. The CDM is just a mass function, which is actually pretty stably reproduced in the simulations. It's the prescription of how you put variables in those simulations that's very uncertain. And so when we talk about absolute normalization and comparison between the two, you need to look at the prescription of variables. In the SEAL cartoon, that's just the CDM cold matter mass function renormalized by some function.
Mm-hmm.
That shape is actually very stable and very well reproduced in the simulations.
Any other questions? If not, let's thank Andy.
All right, and thank you for inviting me. This talk was originally designed also to be the webinar for the X-ray Surveyor, which I believe is now called the LYNX mission. Be that as it may, what all that means is I'm going to put a little bit of emphasis at the end towards what this means for the future. But before I do that, I want to talk to you about observables that a star with a planet around it has that are different than a star that doesn't at least have a close-in planet. And this is sort of a new phenomena from the point of X-ray astronomy. A big difference between science with the next generation of telescopes and the great observatories is behind me now. When we were designing Chandra, there were none of these. And now there are at least 2,000 some odd exoplanet systems, 5,000 exoplanets that are known, and probably every star in the sky has more than one detectable planet around it as we get better at detecting. And the Exoplanet Zoo, as of 2 months ago, looks something like this. We have all the Kepler objects over here, and then we have what you're seeing here is the semi-major axis. So these things are relatively close to the star. Planet mass is over here. These are relatively low mass, and there are lots of these. And then there are some sort of Jupiter and higher mass objects here. We don't go above this line ever, because anything above this line would be a brown dwarf. So this is really the top of the line. Up there is another kind of object. The group over here are Jupiter mass, but also very close to their host star. We call these the hot Jupiters. They're the first discovered, and they're also the easiest to study because they're big and they're close in, and they have lots of different things going on. And in fact, soon after their discovery in '96, there was a problem because you got this big Jupiter very close to a star. You expect some heating coming in from the star side. The whole thing is phase locked, so only one face of the planet ever looks at the star, and you get bloating on that side. But the bloating seen was more than the modelers expected, and modelers know they're always right. So it wasn't a problem with the models. It was a problem with the input, and the extra input needed was not bolometric luminosity. It was X-ray and UV flux, and once that was added in the proper measure, the atmospheric expansion was fully accounted for. But this then meant that you were also going to have photochemistry that wasn't accounted for thermally, that could only occur due to X-rays, and this could lead to the creation of more complex molecules than you might otherwise expect just through normal thermal processes. On the other hand, coronal radiation also could produce rapid photoevaporation and the end of the atmosphere. So it wasn't exactly sure whether stars were going to be a good thing for the long-term evolution of this planet or a bad thing for the long-term evolution of these planets. And this is what the stars look like today. There are about 2,000 exoplanet hosts known. Most of them are in the F, G, and K range, with a recent pileup of M stars that are relatively close. That's good for X-ray astronomy because most of these G, K, and M stars produce X-rays. They have convective zones and they have differential rotation between the radiation area and the convective zone on top, and this is the fundamental source of the dynamo that will give rise to X-rays that we can observe. So these two diagrams are very important to us, and so is the third one at the bottom here. This is the relative size and color of A stars to M stars. Meanwhile, the exoplanets, the hot Jupiters, are always about the same size, which is about 10% of this size. And what that means is that if you have a tiny thing going across this, it might be hard to see, but that same tiny thing going across the M star is going to be much more visible. So M stars become a very good place to look. They also tend to be very close. Now, the other piece I'm indicating on this plot is the HK ratio. This is emission lines of calcium, H and K, and this is an activity indicator. And for many of the non-Kepler sources, this line has been measured, this ratio has been measured. The more active stars are redder, and the less active stars are in blue and green. And when I remove the riffraff, you will notice, here's some active stars here and here and here and here. But there seems to be, just by eye, a few more over in this circle than in this circle, even though there's sort of 2 or 3 times the number of stars here. And that's a hint, at least, that maybe, just maybe, the fact that the planet is hosting a hot Jupiter, or the star is hosting a hot Jupiter, is affecting the star. Now, how can that happen? Well, Steve Saar and Manfred Kuhns, now 15 years ago, realized that stars and planets can interact through 2 different physical mechanisms: tidal interaction and magnetic interaction. Tides we kind of know happen. We're living on a body that is affected by tides. The day now is longer than it was at the time of the dinosaurs because of tides raised by the moon, and this moves the moon further away. The tidal process has to, some level, has to happen. We know this. Magnetic interaction is a little bit fuzzier because that requires field strengths of both items and how those fields interact and whether they're hardly bound, whether the fields are aligned the same. But both of these effects work as R cubed. So in using either of these mechanisms, the planet can affect the host star. And when you go through the details and you look at the magnetohydrodynamic simulations, or you just use analytic models, you can demonstrate that this should give rise to flare-like activity and should give rise to mass loss of the planet, and it might give rise to spin-up of the host star. So what's the evidence for this? And 10 years ago now, Evgenia Shkolnik looked for changes in this H and K line flux from a couple of nearby systems, HD, well, the address is here, HD 179949 and Upsilon Andromeda. And in both of these cases, she was able to identify flux changes in the line with the orbital period of the planet. So if you put this on sort of the 10-day time scale, nothing's phased, but it phases with the orbital period of the planet. That was the good news. The bad news was when they went back a year or 2 later, the signal went away. It's non-persistent. And one can understand this just in terms of the stochastic nature of these stars. Sometimes you're at a high magnetic flux period, sometimes you're not at a high magnetic flux period. But it kind of makes, and this kind of leads back to Andy's talk, some of the statistical signatures of these things don't always show up all the time. So how do you prove that they're real? And Vinay tried to do this. This is a plot from his paper about 10 years ago. And what he did here for the data that existed 10 years ago was he looked at the Rosette allsky survey and the fluxes of every exoplanet host, those that had hot Jupiters close in and those that had planets that were further away. And if you took the statistics and you tried to take account for every variable that they could, they found a very small systematic offset. And Brendan Miller did a very similar study last year. The way he phrases it, he says, there was no correlation because everything that I saw was driven by a few extreme examples. And in fact, what Vinay says in his paper is that this is driven by a few extreme examples. So that for the most part, it doesn't look like that when you look at a statistical sample, most stars at that moment care that they have an exoplanet around them. But occasionally they do. And we know this happens because there are RS-Canvan stars in the sky. And what's an RS-Canvan star? But it's an evolved binary system of low-mass stars. And as the stars change mass, or not change mass, but as they evolve and they change their radius, the orbits evolve. And this is seen in their X-ray flux as a magnetic interaction. These aren't images, but these are models forward folded from observed X-ray data. Going back a step, and let me see if I can do it there. Going back a step, these are models by Ofer Cohen, who just left a couple of months ago. And what he's showing here is that in the frame of the planet is going to see the magnetic field of the star whipping by, and this can start to strip off material from the planet. Or, depending on how the magnetic fields are aligned, that material can be brought in and create a hotspot on the host star. So there are some things we can go looking for if we can find the right extreme system. And one of the right extreme systems seems to be this one, HD 189733. This is actually a binary system with a mass a little bit less than that of the Sun, with a hot Jupiter. And this is more or less what the system looks like to scale. The planet is at about 8R star. The background image here is actually taken from the Sun. This is the Sun during eclipse. And what you're seeing here is the visible corona, and the visible corona of the relatively weak X-ray source of the Sun stretches 8R star. So if you can imagine a system that was 100 times brighter, it's going to be constantly bathed in this fairly heavy coronal emission. So already we have a sense that this is probably going to have some impact on the exoplanet, but my real question is, does it have anything that we can see happening to the star? And for that, we again go back to simulations, this one by Tito Matsaukis. In this particular simulation, we're here on the Earth looking at the star while the exoplanet goes behind and is eclipsed. So in this particular case, when we observe right now, we're not seeing the exoplanet, but we might be seeing some of the material that's being either driven off and blown back into the stellar wind or being drawn in by the magnetic field of the star. And this is what we saw when we've done that. We've done that now, I think we've done 5 times total plus a couple in the UV. Typically, this is the result we get. We don't see any change in the flux when the planet is eclipsed. But very soon after the eclipse, we've seen several times flares of a factor of about 2, usually within a couple of hours, just after the planet has gone behind the host star. And this is very consistent with this model that Tito's came up with early in the previous slide, because what he's arguing is that some material is probably moving forward and creating a hot spot. And remember, what you have when you have X-ray emission on a star is the situation is limb brightened. You see through all of it. So if the hot spot is coming by and if it's especially active, you should see some kind of flaring as it comes around the corner. This last one here was really, really interesting to us for a couple reasons. One, it seemed a little bit late, unless that was the hot spot, but also seemed to go pop several times as it was coming around the corner. And here it looks almost like a stair-step pattern. It seems very regular, both in terms of time and in terms of the decrement between the different echoes. And to us, that brought to mind a damped magnetoacoustic oscillation. If you just imagine that you whip something back and forth, you should see reverberations of that if you're going down a solid tube, or in this case, a magnetoacoustic tube. And the formalism for that is that the step down should have something to do with the density and the temperature and the magnetic field. And if you have the proper X-ray telescope, and we happen to do this with XMM, you should be able to measure the density and the temperature from the spectra, and then you can solve, because this decrement is measurable even by eye, for the magnetic field. And the magnetic field we derive just from this flare on the surface of the star is about 50 Gauss. You could believe that, you could not believe that, but there's an independent verification. ZDI measurements were done of the star as well and got practically the same answer. So now we're fairly certain that this is a magnetoacoustic oscillation, and what we can measure here now by using the sound speed is the length of that loop that gave rise to the flare. And the length of the loop we derive is something like 2 to 4 stellar radii. And this is actually really key, because normally when you see a stellar flare, you're measuring something that's a fraction of the size of the star. On the Sun, it's usually a couple of percent. Big flares seen on young stars tend to be about 10% the size of the star. This is not a scaling with the size of the star, it's scaling with the system. So if this is really about 8R star, we're talking about this kind of configuration. Now, I don't know that the flare was directed at the planet in this case, but I do know from other work we've done that when you get really long loopy flares in young stars, you usually have to have a disk to have the other end of the system, the other end of the loop being drawn to. When you don't have a disk, you don't have really long flares. So the way we describe this system is, or this event, is a bad day for the planet. Something really traumatic is going to happen to the planet. And worse than that, the planet was the main contributor to its problems, because the planet is probably the thing that's driving the excess energy that the star has to give off. So this is something we're going to have to bring forward now, is that when we're evaluating the long-term stability of a system in the, for life or for how the atmosphere is going to evolve, we have to realize that we can't just look at surveys of stars at different ages and say that's the average environment. We have to understand the planet itself might be affecting the environment, especially in the M stars where Dave Charbonneau and his group is working and think is the most likely place to find nearby life. So we're looking now very carefully at Proxima Cen and seeing if it's making its own bad luck right now. Okay, so I've been talking to you about what happens when the exoplanet is eclipsed by the star and what we can learn from looking at that. How about the other side, when the exoplanet is in transit around in front of the star? So this is kind of the normal case that we're now, teaching about in all the textbooks. You have a star that's sitting there, and you have an exoplanet that goes in front of it, and you get a little dip of flux, in this case 3%. This is HD 189733. Katja Papenhager, when she was here as my postdoc and then as a Sagan Fellow, said, well, why don't we do the same thing with Chandra and see what we get? Now, we have to do multiple observations because we don't have a smooth surface behind us. The thing's flaring and bubbling, but we can do some sigma clipping and clean that out. Nonetheless, without very much sigma clipping and cleaning it out, I think you can just look at this data and sort of do a chi by eye over here, and you sort of see that the mean data points are up here, mean data points are over here, and during the transit, the mean data points are down here. We're definitely seeing the transit blocking X-rays coming from HD 189733. And that was actually really surprising. We didn't think the effect would be this big. But when we go, we can actually fit that with, again, a Lim-Brighton model. And what we find is the eclipse depth in the X-ray is nearly 3 times the depth we see in the optical. Well, how do you do that? Means the planet is bigger to X-ray perception than it is to optical light. And that's what this little fuzz is drawn like over here to indicate how much bigger the star is in the X-ray than it is in optical light. Well, how do you do that? Turns out all you need is a little bit of hot gas over the surface of the star. And this is fairly straightforward atmospheric physics. The diameter that you see, or the change in diameter, has something to do with the scale height of the very low mass gas or very low density gas. You can plug in for the density of the gas and the temperature based on the perceived increase in radius and get a value of about 1.75 stellar planetary radii at 20,000 degrees. By the way, there's a little enhancement seen in the UV as well. So in the UV, the planet is about 10% bigger. But in the optical, it's about 75%, or in the X-ray, it's about 75% bigger. I'm going to rush through this very quickly because I'm running out of time. But one can imagine asking, well, how old's this planet, therefore? How old's the star? And the X-rays give us a way to get at that. If you can calibrate X-ray luminosity versus the age of known stellar clusters, and you get this age-activity relation, and we can put HD 189733A on this, and we find that it's about 1 billion years old. But it's a binary, so we should be able to put the M star on the system and find the exact same age. We don't. The M star, which doesn't have a hot Jupiter, is approximately 7 times older. Okay, that's not true. It looks 7 times older. What's happening here, we think, is that the star is being spun up by what you have here is the hot Jupiter spins around much more rapidly than the K star should be rotating. So again, you have tidal angular momentum transfer, but in this case, you're spinning the star up. If that's true, you should be able to go to other exoplanet hosting wide binaries, compare the two stars, and see the effect. And here's one example of Upsilon Andromeda A, which is one of the stars I showed you in the first panel. And there's about a factor of 2 difference in the perceived apparent age. Corot 2 is probably the biggest case, where the secondary that doesn't have an exoplanet host looks like it's about 5-6 billion years old. The primary looks closer to 100 million years old. So that's an extreme case of spin-up. So far, we've done this with about 15 systems. I'm only going to show the first 8 here. The first 8 we only had 3 excess systems. We now have about 6. But what we're finding is where the hot Jupiter host is where the planet is a hot Jupiter, and the star has a relatively thick convective zone, we see this effect. All right. Extremes work in 2 directions. I've just shown you a lot of examples of hyperactivity from one star. There are about 6 or 7 I could have done that for. On the other hand, we have this one, which is an F6 star. It's young. It has a lithium line in absorption. The exoplanet is 10 Jupiter masses, very top of that diagram, and it orbits in 22 hours. This is very close, very massive exoplanet system. No X-rays at all. It's fainter than the very similar star Tau Boo by more than order of magnitude and a half. So what on earth is going on here? Well, it turns out there's been a lie spread upon us by the people who create the dynamo systems and magnetic fields from them. They create great magnetic fields going up very near the surface of the exoplanet or the star. And they look exactly like the spot patterns we think we perceive. But they're showing you the magnetic field at the top of the dynamo. On top of that, there's a shear layer where the star is more radiative. And it's not exactly clear how the magnetic field gets through that shear layer, which is only about 1% of the thickness of the convective zone. So they kind of shrug and say, well, let's just assume it moves through and makes the same imprint. But the models don't actually indicate that. And if you put the parameters of this system with its 10 Jupiter mass planet and its distance here of about 0.02 AU, we actually raise a tide on the surface of this star that's 500 kilometers. Remember, 2 tides a day. That tidal wave is crossing the surface of the star every 10 hours. So any surface shear layer that has to be crossed by the magnetic field is being tremendously disrupted. So even though the star looks like a normal M or F6 star, the magnetic field seems to be quashed. All right, so where are we now? In extreme cases, we think we've demonstrated that there's tidal spin-up occurring. We think we've demonstrated that the planet is bigger in X-rays than it is at other wavelengths. We think we've demonstrated fairly strongly that semi-permanent features can be made to appear on a star because of the planet. And finally, that there are some system scale events that can be generated by the feedback between these two. I'm going to take the last 2 minutes just to talk about what this means for science in the future and for future telescopes. The landscape is going to change a lot starting next year. TESS and then Plato are designed to find every transiting exoplanet system within about 100 parsecs of the Earth. The great thing about these is they'll be bright. That's the idea. So you can go and follow up and do detailed measurements. So if you just look at the Rosette Allsky survey, there's something like 50,000 stars in it. And those 50,000 stars using the Lynx mission should have count rates of over 1 count per second. So you should get fairly good spectra of these things. And about 14,000 of those will have V magnitudes bright enough even for TESS to detect any exoplanets around them. And if you go through all the math, we come up with something around 50 transiting systems, 35 transiting systems that will be within the range of the Lynx mission. The Lynx mission will probably have a microcalorimeter on board, which means that the spectra will not be smooth, continuous things, but will also have, in addition, strong oxygen or nitrogen or carbon lines that we can look in specifically. So in the specific case I just showed you of 189733, this is what it would look like if you had looking only now in the oxygen line. And if the star that went, or the planet that went in front of you was solid-bodied and the same size as the optical planet, we would be able to measure this in 10 transits at about a 3 sigma level. But if it had the extended atmosphere, that extended atmosphere just in the oxygen line would be visible at nearly 10 sigma. And we could do this in oxygen, we could do this in carbon, we can do this in nitrogen, and sulfur, magnesium. And at each...
Are you using absorption on oxygen in the planetary atmosphere here?
In this particular case, yes. We're just...
Do you assume something about the presence of oxygen?
Yes, we're presuming oxygen in the atmosphere. We could also do this again, presuming carbon or nitrogen, and we're measuring to different altitudes, of course, because of the absorption cross sections being much higher at lower energy. So at low energy, we actually can see to lower density in the atmosphere as well. And we did one experiment where we tried, we cranked this up and worked at a factor of 5 of enhanced oxygen and just looked at what that would do to the eclipse profiles. So if there's a strong difference, if there's a great overabundance in oxygen or nitrogen or carbon, we will be able to measure that, and we'll be able to measure the ratios of them to each other. So I think I'll stop there. Thank you. Okay. John.
I didn't understand something you said about the apparent flare just after the planet came out from behind.
Mm-hmm.
Sorry, it sounded as though that had to do with limb brightening because it's optically thin. But I would think a hot spot would be the same brightness all the way when it's on the front half of the star.
I think we're still kind of tossing that back and forth because we're clearly seeing the flare. We've done, I apologize for any English in the audience, we do something we call the English penalty kick test, where we decide, is it more likely, can you statistically prove that one hemisphere is more active than the other because flares happen more active on one side than the other side? How statistically likely is it to always lose a soccer match at penalty kicks when penalty kicks should be a random distribution? So this was exactly looking to see if flares were more common in one hemisphere or the other. And they are, but only at a relatively small level. I think it was 2 sigma so far. So we're trying to do more experiments. So there's 2 things we're looking at. We're trying to see if there are more flares on one hemisphere than the other. But the second is really trying to understand, why do we get this big bump in flux that then goes away very regularly within this sort of 20% window of phase. And that has to do something with how the hot spot must be coming over the horizon. It's not a tremendously hot event. It's an increase in flux that we're seeing. But I understand your point exactly. It's kind of confusing us. Right.
So in this event that you show that these kind of oscillations that you actually try to measure the
Right.
magnetic field, is this the only possible scenario? Because you show this like...
No, not at all. I should really thank Jody Pasquale if he's in the audience. He made a wonderful visualization of one possible thing that might be happening. The other thing is, instead of having a whip, we might have a coiled spring. So you could imagine that this event is a fairly tightly coiled spring that sort of goes the length of the star from pole to pole. That would have the same total length, but never get up very high. All the model here can tell us is what's the distance from one end of the wave to the other end of the wave. And it could be completely straightened out, or it could be completely wound up. And there's no way to know the difference between those two with this limited model.
Other questions? If not, then our speakers.
Yeah. Thank you. No, I like the fact that. Oh,